Okay, so I hope all the concepts on probability are very, very clear, because we are going to apply each one of them over the questions today. Okay. Let's begin the discussion with the first question. We have the first question saying that a bag contains 9 discs, of which 4 are red, 3 are blue and 2 are yellow. The discs are similar in shape and size. A disc is drawn at random from the bag. Calculate the probability that it will be either red or blue. So you have a bag consisting of 4 red, 3 blue and 2 yellow balls. 4 plus 3, 7 plus 2, 9. In all there are 9 balls in the bag. One ball is being drawn. That one ball can be any one of these available 9 balls. That means in my sample space there are 9 members sitting. Fine. 9 possible outcomes are there. Is it clear? Therefore, total number of elementary events in the sample space is 9. Cool. Next I have the discs are similar in shape and size. What this is trying to say is that each outcome is equally likely to occur. Any ball being withdrawn from the bag has equal chances of occurrence. That means if there are 9 balls in the bag, in my sample space there are 9 elementary events, each one of them has equal chance of occurrence, and that is given by 1 by 9. Probability of any ball occurring when you draw a ball from this bag consisting of 9 balls, wherein 4 are red, 3 are blue and 2 are yellow, is 1 by 9. Is it clear? So probability of each of the elementary events to occur is 1 by 9. A disc is drawn at random. Calculate the probability that it will be either red or blue. So let us define event A as red ball is drawn and event B as blue ball is drawn. Fine. What is the probability that either a red ball is drawn or a blue ball is drawn? That means what is the probability that event A has occurred or event B has occurred? What is A or B? It is nothing but the event A union B. What is the probability of occurrence of the event A union B? Here A and B are mutually exclusive. Is there anything to be explained in this line? A and B are mutually exclusive events. See, one ball is being drawn from the bag. If a red ball is drawn, then clearly blue ball is not drawn. So if event A has occurred, event B in that trial can never occur. If a blue ball is drawn, that means event B has occurred, then definitely red ball cannot be drawn because a single ball is being drawn. So when event B is occurring in a trial, A is not occurring simultaneously in that trial. So in no trial can simultaneously A and B occur together. Therefore, A and B are mutually exclusive events. In that situation, probability of A union B, you should be very much thorough with the formula. It is probability of A plus probability of B. What is the probability of occurrence of event A? That means what is the probability of drawing a red ball from this bag of 9 balls, wherein each ball being drawn has equal chance of occurrence? How many red balls are there? 4 red balls are there. So 4 favorable outcomes are there out of the 9 total outcomes. So you have 4 by 9. Or you would have said event A consists of 4 elementary events, which are my 4 distinct red balls, right? They are similar in shape and size, but there are 4 in number. So these 4 are my elementary events favorable to event A. So probability of event A is sum of the probability of each of the elementary events favorable to event A. So it is probability of first red ball plus probability of second red ball plus probability of third red ball plus probability of fourth red ball. Probability of each of the red balls means probability of these 4 elementary events, which is 1 by 9 each. So it is 1 by 9 plus 1 by 9 plus 1 by 9 plus 1 by 9, that is 4 by 9. Similarly, probability of event B is that a blue ball is withdrawn. Now in the bag there are 3 blue balls, right? That means there are 3 elementary events favorable to event B. So probability of event B will be the sum of those 3 probability of elementary events, which is 1 by 9, 1 by 9, 1 by 9. So this will be 3 by 9. This gives you 7 by 9. Is it clear? Pretty easy question. I've just discussed all the concepts behind it so that it is crystal clear to you and stays with you for a longer period of time. Now let's move on to the next one. On her vacations, Veena visits 4 cities, A, B, C and D in a random order. Okay. So she is visiting these 4 cities. What is the probability that she visits A before B and B before C? Now see, there are 4 cities A, B, C, D. Veena is visiting them in random order. What are all the possible orders of her visiting all these 4 cities? Well, Veena is visiting 4 cities A, B, C, D in some order. What are all the orders? What are all the possible orders? She can visit first city A, then B, then C, then D. First A, then B, then D, then C. Or first A, then C, then B, then D. First A, then C, then D, then B. Fine. Or first A, then D, then C, then B. Or first A, then D, then B, then C. These orders she can follow of visiting the 4 cities. Fine. Or what she can do is she can first visit city B, then C, then D, then A. B, C, A, then D. Then B, A, C, D, B, A, D, C. B, D, A, C, B, D, C. Fine. In these orders, she can visit the 4 cities. Or what she can do, first she can visit city C, then B, then A, then D, C, B, D, A, C, D, A, B, C, D, B, A, B, D and this. So in these ways also she can visit the 4 cities in this order also. More orders, first city D, then A, then B, then C, D, A, C, B, D, C, A, B, D, C, B, A, D, B, A, C, D, B, C, A. Fine. These are all the possible orders in which she can visit the 4 cities. That's it. It's exhausted. So here if you can count 6 plus 6 plus 6 plus 6, there are 24 possible orders. And this is what is my actual sample space, which is the set of all possible outcomes. And that is nothing but the set of these 24 possible orders in which she can visit the 4 cities. One more way in which you could have obtained the number of members in the sample space. She is visiting these 4 cities in a random order. It is almost like saying, how many possible orders are there for Veena to visit these 4 cities? Or rather than that, I can say how many ways are there in which in 4 distinct places these 4 distinct letters can be arranged. These 4 distinct letters in 4 distinct places can be arranged in 4 factorial ways, which itself is 24. Each of the ways in which these 4 letters can be arranged in these 4 places is going to describe a particular order in which Veena is visiting the 4 cities. This is one of the ways in which 4 letters can be arranged in 4 places. This is another, this is another, this is another, and so on. Each of these arrangements of these 4 letters in 4 places is describing you the order in which Veena is visiting these 4 cities. So this was also one way in which you could have thought of obtaining the very number 24, which is the total number of elementary events associated to my random experiment. Further it says, what is the probability that she visits A before B and B before C? So if I am saying, say my event E is there, that Veena visits A before B and B before C. How many elementary events are favorable to this event? A before B and B before C, A before B, B before C. This is A before B, but B is not before C. A before B and B before C. After that I have A before B and B before C. That's it. None of the other orders are there which describe Veena visiting A before B and B before C. Only these 4 are there, A, B, C, D. Then you have A, B, D, C. Then you have A, D, B, C and D, A, B, C. So what is the probability of occurrence of event E, which describes you the probability of Veena visiting A before B and B before C? It is what? Well, over here, of course, you have to assume that each of the elementary events has equal chances of occurrence, and therefore each of these orders have probability 1 by 24. There are 4 elementary events favorable to my event E, so it will be 1 by 24 plus 1 by 24 plus 1 by 24 plus 1 by 24, which will be the probability of event E, that is 4 by 24. Fine, or rather than that, you can say number of favorable outcomes is 4, total number of outcomes is 24, so 4 by 24, that is 1 by 6. That's the probability. Clear? Let's move on to the next. We have an experiment consists of rolling a die and then tossing a coin. So a die is rolled, and when one die is rolled, one coin is tossed. Okay. So one die is rolled and one coin is tossed if the number on the die is even. If the number on the die is odd, then the coin is tossed twice. Write the sample space for this experiment. It's very easy. Case 1, number on the die is even. Number on the die is even. That means it is 2 or 4 or 6. Only 6 outcomes occur in a die. 1, 2, 3, 4, 5, 6. Out of that, 3 are even. If number on the die is even, then the coin is tossed just once. So head can come or tail can come. What is the sample space? Then possible outcomes are 2 on the die, head on the coin, 2 on the die, tail on the coin. 4 on the die, head on the coin, 4 on the die, tail on the coin. 6 on the die, head on the coin, 6 on the die, tail on the coin. That's it. Because number which has occurred on the die is either 2 or 4 or 6. There are the 3 possible outcomes wherein I can say the number that has occurred is even. And when the number that has occurred is even, then the coin is tossed only once. So either head can come or tail can come. So one I have 2, 4 and 6, other I have head and tail. So in what all ways can I can say that the possible outcomes are going to occur if I consider the outcomes of both the situations of the die as well as the coin. 2 can come along with head, or 2 with tail, 4 with head, 4 with tail, 6 with head, 6 with tail. This is going to actually mean that even number on the die and head or tail on the coin. Fine, because only one coin is tossed. Case 2, number on the die is odd. So this number is 1 or 3 or 5. In this situation, the coin is tossed twice. So when the coin is tossed twice, what are the possible outcomes? Head, 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 tail, tail, head, tail, tail. These are the 4 possible outcomes. So then, together the possible outcomes will be, then the possible outcomes are 1 on the die, head, head, as the one possible outcome that you can get when you toss a coin twice. 1 on the die, this outcome, 1 on the die, this outcome, 1 on the die, and this outcome when you toss the coin twice. Or you can get this on the die, this on the 2 coins, this on the die, this on the 2 coins, this on the die, this on the 2 coins, this on the die, this on the 2 coins, this on the die, this on the 2 coins, this on the die, this on the 2 coins, 5 tail head, 5 tail tail. And therefore, overall, when I want to write the sample space, it will be this union this. So my overall sample space will be what? So my sample space is this, that is 2H, 2 tail, 4H, 4 tail, 6H, 6 tail, 1H, H, 1 head tail, 1 tail head, 1 tail tail, 3 head head, 3 head tail, 3 tail head, 3 tail tail, 5 head head, 5 head tail, 5 tail head, 5 tail tail. That's my sample space. Clear? Moving to the next, we have a coin is tossed 3 times. Consider the following events. Event A is given to you that no head appears, then it is given that exactly 1 head appears, then at least 2 heads appear. Do they form a set of mutually exclusive and exhaustive events or not? Let's try to decode what are all the elementary events and how many are favorable to each of these events A, B and C, and then talk about them being mutually exclusive or exhaustive. A coin is tossed 3 times, so my sample space is head, 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 tail, head, tail, head, head, tail, 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 head, tail, 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 head, tail, tail, tail. Or I should write tail, head, head. Fine. 8 elementary events. No head appears. No head only appears in this elementary event. So there is only 1 elementary event favorable to event A. Then at least this exactly 1 head appears. Exactly 1 head is here. Exactly 1 head is here. That's it. Nowhere else is there exactly 1 head. So it is tail, head, tail, 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 head, and here also head, tail, tail. Exactly 1 head. Then C, at least 2 heads. This, 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 this. So it is head, 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 tail, head, tail, head, tail, head, head. Now I am talking about, are they forming a set of mutually exclusive and exhaustive events. So for exhaustive, their union should be equal to the entire sample space. So if I talk about A union B union C, I will have this all coming. So 1, 2, 3, 4, 5, 6, 7 and 8. All 8 distinct outcomes are there which are going to come when I will be forming the set A union B union C. So clearly this is equal to my sample space. Talking about them being mutually exclusive means I am wanting to test the pairwise mutual exclusiveness. What is A intersection B? A intersection B, nothing is common, 5. B intersection C, B and C, absolutely nothing common, again 5. A intersection C, common between A and C, absolutely nothing, so again 5. So this means that A, B, C form a set of mutually exclusive and exhaustive events. So they are mutually exclusive as well as mutually exhaustive. Clear? Next we have 3 dice are thrown together. Find the probability of getting a total of at least 6. Now please try to understand, it's very difficult to write the sample space explicitly in here. 3 dice are thrown. On the first die you can get outcomes from 1 to 6. On the second die you can get outcomes from 1 to 6. On the third you will be getting outcomes from 1 to 6. Fine. So if first die is giving you 6 possible outcomes, second is giving you 6 possible outcomes, third is giving you 6 possible outcomes, that means all 3 of them rolled together are going to give you 6 into 6 into 6, that is 216 outcomes in total. Of course, it's impossible for us to write all the 216 possible outcomes, and there is no need as well. I have just understood that number of elements in the sample space is 6 into 6 into 6, that's 216. So there are 216 in total elementary events associated with this random experiment. Clear? Find the probability of getting a total of at least 6. That means when the possible outcomes you are considering, there is an outcome on the first die, outcome on the second, outcome on the third. These outcomes are ranging from 1 to 6. I am wanting to talk about the probability of occurrence of those outcomes which are going to land me getting a sum as 6, at least 6. That means when I add the outcomes on all the 3 dice, I get 6, at least 6 as the sum. So A is the event of getting sum at least 6. Now out of 216 outcomes, getting a sum at least 6, well, If 1 comes on the first die, 4 on the second and 1 on the third, this is one of the outcomes which can give me 6 as the sum. Then 2 over here, this will be giving me 7 as the sum and all the possible ways in which I can permute them. 2, 4, 1, 1, 4, 2 or 4, 1, 2 or 4, 2, 1, all these. So if you can understand, if in place of 2 I write 3, 8 is the sum. So I don't know how many I will have to actually write these ordered triplets showing me all the possible outcomes which can give me at least 6 as the sum. That would be a pretty large number, right? So what instead we do is we move in an alternative fashion. My aim is to find probability of A. I know probability of A plus probability of not A is 1. So probability of A can also be obtained by removing probability of A bar from 1. So let's compute probability of A bar. First of all, what is A bar? If A is getting sum at least 6, this means getting sum less than 6. Now minimum outcome that you can get on all the 3 dice is 1 each. 1 on the first die, 1 on the second die, 1 on the third die. That would be the minimum outcome you can get, right? So in that case, the sum is going to be minimum, which is 3. So minimum sum that you can get when you add the outcomes on the 3 die is 3. After that you can get 4, 5, 6, 7, 8 and so on. So if the sum is less than 6, that means the sum can be getting sum 3 or 4 or 5. That's it. So this is a limitation, right? This is a finite thing. Either 3 sum or the sum is 4 or the sum is 5. But when I talk about at least 6, it would be 6, 7, 8, 9, 10 and so on. Fine. So it's better to proceed in this fashion. Now what all do you think are the possible outcomes which can get me sum as 3, sum as 4, sum as 5? Let's see. 1 on the first die, 1 on the second die, 1 on the third die is going to give you 3 as the sum. That's it. No other possible outcome can give you 3 as the sum. Then 1 on the first die, 2 on the second, 1 on the third will give me 4 as the sum. 2 on the first die, 1 on the second, 1 on the third will give me 4 as the sum. 1 on the first die, 1 on the second, 2 on the third will give me 4 as the sum. Next, 2 on the first die, 2 on the second, 1 on the third will give me 5 as the sum. 2 on the first die, 1 on the second, 2 on the third will give me 5 as the sum. 1 on the first die, 2 on the second, 2 on the third will give me again 5 as the sum. Or I can get 1 on the first die, 3 on the second and 1 on the third. This will also give me 5 as the sum. 3 on the first die, 1 on the second, 1 on the third, 1 on the first die, 1 on the second, 3 on the third. That's it. These are all the possible outcomes which can give me 3 or 4 or 5 as the sum. That's it. So these are my favorable outcomes to my event A bar. So probability of A bar will be number of favorable outcomes, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 10 upon total number of possible outcomes, that is 216. So probability of event A will be 1 minus 10 upon 216. You can always evaluate this. This is the probability that the sum is going to be at least 6. 1 minus the probability of sum being less than 6. Clear? Moving to the next, we have find the probability that when a hand of 7 cards is drawn from a well shuffled deck of 52 cards, it contains all kings, 3 kings, at least 3 kings. Okay. So one hand is being inserted in this well shuffled deck of 52 cards, and you are in one go in that hand withdrawing 7 cards. Fine. Now, first of all, let's talk about the number of elementary events in my sample space. You are withdrawing 7 cards in one go from a well shuffled deck of 52 cards. How many possible outcomes can be there of these 7 cards being withdrawn? That means in how many ways can you draw 7 cards out of 52 distinct cards? That is number of ways in which 7 cards can be chosen out of 52 distinct cards, that is 52C7. That's the total number of elementary events in my sample space. Now it is saying all kings. That means the 7 cards that I have withdrawn, all the kings have been withdrawn. Okay? How many kings are there in a deck of 52 cards? 4 kings, king of spade, king of diamond, king of hearts, king of clubs. That's it. So if all the 4 cards have been withdrawn, that means out of 7 cards, 4 are definitely kings. And rest 3 can be any 3. Rest 3 can be any 3. The 4 kings have been withdrawn. Rest 3 can be any 3 out of the rest of the 48 cards, because 4 have been withdrawn as the 4 kings. So probability that all kings have been withdrawn, how do you write it? That is probability of what event? Basically all kings have been withdrawn. Total number of elementary events is 52C7. What are the favorable ones? Let's see. All kings, there are 4 kings, 7 cards I am withdrawing. So first of all, out of 4 kings in well shuffled deck of 52 cards, all the 4 kings can be chosen in 4C4 ways. And means multiplication. And I am now left with 48 cards in the bag. Out of those 48 cards, because 4 kings have been withdrawn, out of those 48 cards, I am now interested in withdrawing 3 more so that I can complete my set of withdrawing 7 cards. 4 I have withdrawn as 4 kings. 4 kings can be withdrawn from a set of 4 kings, because there are overall 4 kings in my well shuffled deck of 52 cards. 4 kings can be withdrawn from a set of 4 kings in 4C4 ways, and there are more 3 cards to be withdrawn. So I am left with now 48 cards. Out of 48 cards, 3 cards can be withdrawn in 48C3 ways. So these are the number of ways in which all the kings will be withdrawn. Rest you will be left with 3 cards which will be withdrawn from the leftover 48 cards. So in these many ways, I can withdraw all the 4 kings in my draw of 7 cards. Fine. This you can very easily evaluate. After that I have 3 kings. Now total is 52C7. 3 kings. I have 4 kings in my well shuffled deck of 52 cards. So 4C3 is the total number of ways in which 3 kings can be withdrawn out of 4 available kings. And I am not just withdrawing 3 cards, I am actually withdrawing 7 cards. Rest 4 cards will have to be non-king cards, right? So now 48 are non-king cards. Out of these 48, I can withdraw the 4 leftover cards, because 3 I have withdrawn as kings. Rest 4 will be withdrawn in 48C4 ways. So 3 from here, 4 from here, 7 cards such that 3 are kings can be withdrawn in these many ways. These are the total number of ways of withdrawing 7 cards. So this is my probability. Then you have at least 3 kings. At least 3 kings. Now at the max there are 4 kings. Overall there are 4 kings. So at least 3 kings means either 3 kings or 4 kings. So either 3 kings will be withdrawn or 4 kings will be withdrawn. Right? They both are mutually exclusive events. So probability of 3 kings plus probability of 4 kings. Probability of 3 kings is this. This is probability of 3 kings, this is probability of 4 kings. So you can just compute and add them, you will be getting your answer. Cool enough? Moving to the next, we have what? 2 students, Anil and Ashima, appear in an examination. The probability that Anil will qualify the exam is this. Ashima qualifies is this. Both will qualify is this. Find the probability that Anil and Ashima both will not qualify the examination. So E event, let me take event E, that Anil qualifies the exam. Fine. And let me take F as Ashima qualifies the exam. What is probability of Anil qualifying the exam given? It is 0.05. And what is the probability of Ashima qualifying the exam given? It is 0.10. I am being asked what is the probability that Anil does not qualify and Ashima does not qualify. Is it cool? This event occurs and this event occurs, that means E bar occurs and F bar occurs, that means negation of E occurs and negation of F occurs. Together, that means Anil does not qualify and Ashima does not qualify the exams. This is the event whose probability I need to compute. This is probability by De Morgan's law, E union F whole bar, which is 1 minus probability of E union F, which is 1 minus probability of E plus probability of F minus probability of E intersection F. Probability of E is 0.05 plus probability of F is 0.10, probability of E intersection F is this 0.02, that is both qualifying. This happens to be 0.05 plus 0.10 is 0.15. So 0.15 minus 0.02 is 0.13. This happens to be your very probability of both Ashima and Anil not qualifying the examination. So this is 0.87. Fine. Next you have what? Probability that at least one of them will not qualify. So probability of at least one of them not qualifies is same as saying 1 minus probability of both qualifying. Right? Probability of event A is 1 minus probability of not happening of event A. So not happening of this means this. At least one of them qualifying, its negation is. At least one of them not qualifying, its negation is both are qualifying. This is 1 minus, what is probability of both qualifying? 0.02 given in the question. So 0.98 is the answer for the second part. And then it says only one of them will qualify. That means Anil qualifies and Ashima does not qualify, or Anil does not qualify and Ashima qualifies. Or is changed to union, and that's the event I need to compute the probability of. Both these are mutually exclusive, so this is probability of E intersection F bar plus probability of E bar intersection F. What is probability of E intersection F bar? See, if I talk about the Venn diagram, that's the sample space, this is E, this is F. E intersection F bar is this. This is same as E minus E intersection F. So this is equal to probability of E minus probability of E intersection F. Similarly, E bar intersection F is this. This is E bar intersection F, and this is E intersection F bar. This is again F minus E intersection F. This is probability of F minus probability of E intersection F. So what is the answer? Probability of E is 0.05 minus probability of E intersection F, which is 0.02, plus probability of F is 0.10, again minus 0.02. This gives you 0.11 as your answer. Clear? Let's move to the next. We have, if A, B, C are three events associated with a random experiment, prove this. Probability of A union B union C. It's pretty easy. It's just a matter of computation. Let's do that. A union B union C. If I take B union C to be equal to E, this will be probability of A union E, which happens to be probability of A plus probability of E minus probability of A intersection E. Fine, let's just try to resolve this. This is probability of A. Probability of E means probability of B union C minus probability of A intersection B union C. Cool. This is probability of A plus, what is this? Probability of B plus probability of C minus probability of B intersection C. Let's resolve this part. This is probability of by the distributive property of intersection over union. This is A intersection B union A intersection C. So I have probability of one event union another event. I know how to resolve this. Let's keep the rest of the terms as it is. Okay. Now I have probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection A intersection C. So A intersection B intersection A intersection C is A intersection B intersection C, and you have got your answer. Probability of A plus probability of B plus probability of C minus probability of B intersection C minus probability of A intersection B minus probability of A intersection C plus probability of A intersection B intersection C. I have opened up the brackets, and that's it. Okay? Next question says find the probability that a leap year selected at random will contain 53 Sundays. Now a leap year consists of 366 days. If you divide it by 7, you will be getting 52 weeks. You will be getting 52 weeks, and remainder will be 2, implying 2 days. So if in a leap year there are 52 weeks, that means 52 Sundays are definitely going to occur. Rest you are left with 2 days. So my sample space is going to consider all the possibilities of those 2 days. So one possibility can be that it's a one day is Monday and other day is Tuesday. Second possibility can be one day is Tuesday, other day is Wednesday. Another possibility can be one day is Wednesday, other is Thursday. The next possibility can be one day is Thursday and other is Friday. Another possibility can be that one day is Friday and another day is Saturday. And then I can have Saturday and Sunday. Or I can have those 2 days being Sunday and Monday. So my sample space is the set of these 7 outcomes. That's the sample space. 1, 2, 3, 4, 5, 6 and 7. What are the possibilities of those 2 days which occur in a leap year apart from the 52 weeks, because there are 366 days? So those 2 days can be these two, these two, these two, these two, these two, these two, or these two, coming from here. Suppose A is the event that leap year contains 53 Sundays. Now obviously, if a leap year is definitely containing 52 Sundays, for it to contain the 53rd Sunday, at least one day, or actually just one day out of the 2 days which are there in a leap year should be a Sunday. 52 weeks are always there in a leap year, so 52 Sundays are definitely going to occur. For a 53rd Sunday to occur, out of those 2 days which are sitting over there extra in a leap year, one of them has to be a Sunday, right? So that means out of 2 days apart from 52 weeks in a leap year, one is a Sunday. That means out of all these possibilities of those 2 days, which are the possibilities which are favorable to this event? Only those which consist of one day being a Sunday. So one day being a Sunday is here and one day being a Sunday is here. So only these 2 elementary events are favorable to this event, that is 6 and 7. Fine. Occurrence of each of these outcomes is equally likely, and therefore if there are 7 possible outcomes, each of these outcomes has 1 by 7 probability. So what is the probability of occurrence of event A? It is sum of the probabilities of each of the elementary events favorable to event A, that is probability of this and plus probability of this. Probability of occurrence of this event is 1 by 7. Probability of occurrence of the next is also 1 by 7 because they have equal chances of occurrence. So your answer is 2 by 7. Okay? Next question says that a committee of 2 persons is selected from 2 men and 2 women. Okay? So there are 4 people in total and a committee of 2 persons is selected. So first of all, please understand, 2 persons can be selected out of 4 persons in 4C2 ways. Therefore, if I am considering my sample space to be the set of all those possible ways in which two persons can be selected, then definitely number of members in the sample space is 4C2, which is 4 factorial upon 2 factorial into 2 factorial, which is 6. Clear? What is the probability that the committee will have no man? So let A be the event that no man is selected out of the 2 people which are selected out of the 4 available persons, out of which 2 are men and 2 are women. If 2 are men and 2 are women, and I am selecting 2 people out of these 4 such that no man is selected, then clearly that means that both the selected persons are women, right? There are in total 2 women and I want to select 2 women. So 2 women can be selected from the available 2 women in 2C2 ways, which is just one way. So that means both selected persons are women, right? So what are the total number of ways of selecting 2 people out of available 4? It is 4C2. And how many other ways in which you can select no man when you are selecting 2 persons out of the available 4? Well, because the fashion is that there are 2 men and 2 women, that means you only want to select women so that no man is selected, and you want to select 2 persons also. That means you will be ending up selecting both the women that you have. So out of 2 available women, 2 women can be selected in 2C2 ways. So this is 1 upon 6. Next you have event B, which says 1 man is selected. 1 man is selected. Now there are 2 men and 2 women, 2 people are selected. One is for sure a man, exactly one is a man, so other has to be a woman, right? That means 1 man and 1 woman is selected. So total number of ways in which 2 persons can be selected from 4 is 4C2, right? 1 man is selected and 1 woman is selected. In total you have 2 men, out of that 1 man can be selected in 2C1 ways. Once this man has been selected, because you are selecting 2 persons, another one is left to be selected, and out of 2 women, 1 woman can be selected in 2C1 ways. So there are 2 men and 2 women, 1 man is selected and 1 woman is selected. These are the total number of ways in which 1 man and 1 woman can be selected from available 2 men and 2 women. Is it clear? Then you have event C. You can compute this. What is 2C1? It is 2. 2C1 is 2, right? This is 6. So this is 4 by 6, that is 2 by 3. Fine. 2C1 is what? This is 2 factorial upon 1 factorial into 1 factorial. So it is 2 only. Fine. So you have 2 into 2 upon 6. Next I have event C. Event C is 2 men. 2 men are selected. As it is, I want to select only 2 persons and both I want to select men. Available I have only 2 men. That means from the available 2 men I will be selecting both of them. So clearly, just like in event A, out of 2 men can be selected in 2C2, that is one way. And here I have what? 4C2. That's the total number of ways in which 2 persons can be selected. Fine. 2C2 is 1 and this is 6. So this is my required probability. Clear? That is what completes the discussion over all the questions. Okay, so please revise them very nicely. All the concepts have been covered in this question. Sit with them, solve them by yourself. You can tally with the solutions anytime you want. That's it from my side. Take care. Your next session would be beginning, right? Your next session would be beginning approximately after half an hour. So let me just confirm the timings for the next session. And then you can join that lecture. That's it from my side, guys. Thank you.